Well, thanks a lot for the invitation. Very nice, interesting workshop. So let me start by saying a few words about the title. Because among the activities that I follow in quantum information theory in Pavia that are quite wide in topics, I mean, ranging from thermodynamic aspects, communication, computation, intelligence theory, and so on, open quantum systems. I chose this particular topic because we have a very interesting interplay between the.
Sorry, there is a bit of room in the of noise in the room, so it's.
Temevo.
Yes.
Okay, no problem. So I was saying that I chose this particular topic because we had a very interesting interplay between theoretical investigations that we carried out and the photonic experimental verification. So I will first tell you about this in this talk. So this is the reason why I decided to focus on this, because I think it's a very interesting example of how quantum information theory aspects can be linked in a very productive way to photonic experiments. And so I will talk about this quite recent work that we did in Pavia. In Pavia, we work on the theoretical aspects together with Giovanni Chesi, who is here in the audience, and Lorenzo Maccone, and we collaborated with the experimental group of Christine Silver, born in Paderborn. Okay, so this is a very brief outline of what I'm going to talk about. So part of the topic is about entropic uncertainty relations. We will start with a reminder of what it means, of course, in the simplest case of observables, and then we see what happens when we increase the number of observables and increase the dimension. Then I will tell you about the experimental verification in photonic systems and the unexpected new results that we had from this. That it's, I mean, something that we call complementarity-based complementarity. And in the end, I will see how this kind of techniques can be used for the study of entanglement, and in particular to detect entanglement by designing by inequalities based on these quantities. But don't be too scared, so I'll try to really review the main concepts. So when we talk about uncertainty relations, these are linked to the concept of complementary observables, right? Like position, and momentum, typically. And so let me just remind what we mean precisely in a system in generic finite dimension. So we mean that have two complementary properties when, if one knows exactly the value of one of them, all the possible values of the other property are equally large. And so this means, okay, here we have the, okay, here is the pointer. So this represents two observables, A and C. These are the eigenbases. And what happens is that we have complementarity when this condition is satisfied. So this is the modulus square of the scalar product of any basis state of the first observable and any basis state of the second. And so this must be equal to one of the D, is the dimension of the system that we are considering. And this must hold for all the possible basis states. So in this case, we talk about complementary properties, or also in a different terminology of mutually unbiased bases. So the simplest case in dimension 2, so the case of qubit, this corresponds just to the x, y, and z sigma vectors. Okay, so as I was saying, we want to see how to describe uncertainty relations. Maybe you are used to the usual case where uncertainty relations are formulated in terms of product of variances. While here we focus on entropic uncertainty relation. So we don't use variances as it is very but entropic quantities. And I will show later why. Our main ingredient is the Shannon entropy, so it's defined here. And this is, it's an entropic function of this pi, which is a probability vector. So if we measure an observable described by this basis vector, these are the modulus squares, so they are the probability having the result J. So this is the usual classical entropy function. Okay, so this is the simplest entropic uncertainty relation, where we have these two complementary observables. And you can see here that if we take the sum of the corresponding entropies, we have this lower bound. This lower bound, which depends explicitly on the dimension of the system. So this is the logarithm base 2 of the dimension. And the interesting thing is that this bound, as you can see, is state independent. This fixed depends on the dimension, and it's tied for the two mutual unbiased spaces. So it means that there are states that really achieve this minimum value. And these states correspond to eigenstates of one of the two observables. Again, the simplest case of qubits, we can take, for example, X and Z as complementary observables, and we can see that the lower bound is 1, and it's achieved, for example, by states 0 and 1, which are eigenstates of sigma z. And the interesting thing about using the entropy as a big merit is that it's very easy to increase the number of complementary properties, not having just 2, but more than 2. So what we can study is this. So if we have n observables complementary, we can now take the sum of the corresponding entropies, and find some lower bounds that in general are functions of the dimension and of the number of observables that we are considering. We know that the number of mutually unbiased spaces cannot be larger than p plus 1. We also know that in prime dimension we can reach plus 5. Okay, so the known values in the literature for two complementary properties, everything is very simple, and when we increase the number of mutually unbiased spaces, things become more complicated. In particular, in the literature, there were known bounds, but not always tight. So we decided to work on this, and we started by the simplest case. So by increasing the dimension of the system, in the case of qubits, everything is well known. And this is the corresponding entropic uncertainty relations with the three observables, which we can take X, Y, and Z, and this is well known. And so we wanted to see what happens if we increase the dimension. So here we have these simple cases when we go from dimension 3 and we take 3 and 4 complementary observables. We cannot have more than 4 because this is 3 plus 1. In dimension 4, we can have 3, 4, and 5. Dimension 5, 3, 4, 5, and 6. Okay, and this was already contained in this paper that was published some time ago. So let me show you very quickly. So this is the case of 3. This, just to have an idea of what happens and how you can describe these spaces. What you have typically is this complex factor, which depends on dimension. And we can see here that, for example, if we take 3 observables, this is the lower bound. If we take eigenvectors of one of the nuclear magnetic spaces, which are the ones that saturate the phase of 2. But this is not the lowest bounds that we can have, because we can have these tight bounds, which are given by these two forms. And this is what was the interesting part, is that the optimal states, by optimal I mean the ones that with the minimum value, are not eigenstates of one of the observables, but are given by this specific form. They are superpositions of just two of the basis states in the three-dimensional system. Okay, so we can also study the similar situation in dimension 4, and again we found these tight bounds for 3, 4, and 5 observables. And again, the optimal states are not eigenstates of any of these bases, but they are states of this form. And we also studied the case of dimension 5, where again we find all these bounds. Here we have the case of 3, 4, 5, and 6 bases. 6 is the maximum. So here. The optimal states here, the situation was a bit mixed, because as long as we have 3 bases, then the optimal states are the eigenstates of one of the 3, like in the case of 2 complementary properties. But if we increase this number and we have 4, 5, and 6, we have that the optimal states are particular superpositions of 4 eigenstates from the computational basis. So they have, for example, a form like this. So you see it's a superposition of 4 components. Okay, so this was the theoretical part, and then we wanted to see if we could demonstrate experimentally, verify these findings. And we were collaborating with, as I said before, with the group of Christine Silverton in Barcelona, because we were involved in the European project together. And they were interested in the experiment. So the experiment was done in Paderborn in a photonic platform where the encoding was done on using temporal modes. And so this is the scheme that was used. I mean, we did the theoretical support, of course, and this is an example of what was found. So here we have dimension 3 and 3 complementary properties, 3 different bases. And you see here they are, I mean, the colored one are the experimental data. So this is the minimum, the lower bound, and this corresponds to the optimal state, the triangles, while here we also have randomly generated state. So this was this result in agreement with this uncertainty relation, which is one of the ones that I showed you before. Okay, so this for dimension B, then we started increasing the dimension. And dimension 4, in dimension 5, we had a problem. So we had a problem because they could find some states that violated our lower bound. And so we were worried. Why? Because, of course, we thought, well, maybe there is a mistake in our calculation, or maybe there is something wrong in the experiment. And so there was a period where things were not very clear. Nobody knows about this. And while then we found out that actually there was no mistake anywhere, but they were simply using some bases in the experiment which were different than the ones that we used in the theoretical results. But this was a bit subtle because this happened in dimension 5. Because what we did when we studied this problem theoretically was somehow to assume a symmetry. So in the sense that we thought, okay, we take 3 complementary properties, we know that they are nuclear bias bases, and then, I mean, whichever, I mean, there are 6 of them, and any triple for us would be the same. But indeed, it was not. It was not, and the symmetry is not there actually. And in dimension 5 and for 3, this is the only example where we found this problem, which is a new finding. I mean, it was a problem at the beginning, but then it was an interesting discovery. So what happens is that this is the bound that I showed before, when I have A, B, and C. So these 3 bases, this is the lower bound. But if I take the other 3 bases, so D, E, and F, I get something which is lower. And this is what they found in the experiment. And at that time, we didn't manage to explain. And you can see here the difference. So instead of 4.64, we had 4.43. And these are the states that separated this. So it means that, okay, we have complementarity, but in terms of these entropic uncertainty relations, I mean, the basis or the choice of set of bases is not the same. So we can have these discrepancies, which is very nice also from a theoretical point of view and a bit unexpected. And here you see the experimental results of the two cases. So in terms of the entropic uncertainty relation, so this is the blue bound here, and this is the red bound. And what we also checked was what happens in terms of variances. We said, well, maybe it's a peculiarity only of the entropic quantities. But this is not the case. So if you also, compute the variance, we have these two different bounds, by picking up the same triplet of properties. And these are also all the possibilities in this set of 6 bases of how you can pick up triplets, and you can have always the blue results or the red results. So these two different things. Okay. This is the paper, and here we have a distribution of the corresponding states corresponding to the two cases before in terms of entropic quantities and of the sample sizes. Okay, so then, in this second part, if I can find time, I will also show how we can use, these entropic uncertainty relations are interesting per se from their fundamental point of view, but they can also be exploited, for example, in the context of entanglement detection. So what do we mean by this? Let's start from this very simple scenario where we have here a source of entangled states, so it's a bitemporal case, and we have two systems, one is system 1 and this system B, and this system 2, sorry, and here we assume that on system 1 we can measure either A or C, and they are complementary in the sense that and on system 2 we can measure either B or D. So we have these pairs of mutual and spaces. So all together, we assume that when system 1 we measure A, on system B we measure B, while when we measure C on system 1 we measure D on system 2. So together we have these two possibilities. So we measure A tensor B on the composite system, or C tensor B on the composite system. And also on the composite system, these two observables, of course, are complementary because they are complementary. Okay, so what we can do is to, again, find some entropic relations. So here we compute the entropies of the global observables pertaining to the two systems, so the entropy of AB and AC. And what happens is that we can see that as long as we keep just two options, so two complementary properties, we have this condition. So if we minimize this value, so this is the sum of the joint entropies, this is equal to the sum of the local entropies, so minimized over the local states. And this was found in this paper, and it's somehow an additivity properties that holds when we have just two complementary. If this holds, then of course this is not used to detect entanglement property of the composite system, because what happens globally is lower bounded by the local. But the interesting thing is that this holds as long as we consider just two observables. So what we wanted to see is what happens if we increase, again, in the same scale as I showed before, the number of complementary observables. And what happens here, we can see that the additivity of this kind of quantities does not hold anymore, and this is good news. And in particular, we could see that for bipartite system, if these are the single system lower bounds, we can see that if we take the sum of the entropies for the joint case for L properties, this for a separable state is lower bounded by the sum of the local terms. So this means that if this inequality is violated, then we have some entanglement in the system. So this also leads a way to formulate some inequalities based on these entropic quantities that detect the presence of inequality. Okay, this was for the bipartite case. I mean, we can also generalize this to the case of the multipartite system, and in particular, this is what happens for a tripartite system. So for a biseparable state, we have this lower bound, where this F1 is the single system entropic uncertainty relation lower bound, and F2 is the system. If this inequality is violated, then we know that we have genuine multipartite system. Okay, and this is the reference of this work. Okay, I just summarize so I can conclude. So what was the main content of this work? So we derived that more general relations of entropic uncertainty relations that were not present in the literature, with 5 bounds in dimension higher than 2, so 3, 4, and 5, more than 5, and it was already difficult for 5. So we stopped here, for example. For the moment, I defined count bounds and optimal states. I showed you the experimental verification, where we get this very interesting, really interplay and interaction with the experimentalists in this photonic platform, which allowed us really to find some new theoretical results. And we could prove this new aspect, which we name complementary based complementarity, which means that the degree of complementarity depends in some instances, and in the case of dimension 5 and 3 observable that we showed here, on the explicit form of the basis that are considered. And then, the last part was on these additivity properties that call for 2 observables that can be overcome if is the number of observables, leading to a new way to detect the entanglement based on the violation of inequalities based on this. Okay, so I'm at the end. Thank you.